So today we will be talking about two important invariants on manifold. One is the torsion and the other is the curvature. So torsion and curvature. And both these invariants are related to a connection. When we change the connection, these invariants will change. So torsion and curvature of a connection. On a manifold, of course. So as usual, M denotes the manifold, P denotes a point on the manifold, and U denotes a neighborhood. So these are some standard symbols that we have been using all along. So we know that if we are dealing in Rn with the derivatives, partial derivatives, so what we know is that if you consider the second order derivative of any function which is differentiable of order at least 2, then we see del xi, del xj, that these two derivatives commute. This happens for a function whose order is more than 2, differentiable order is more than 2. But the same thing does not happen on a manifold. For example, if you consider the derivative, second order derivative like this, given a function f, if you differentiate along y and then differentiate the function yf along x, this may not be same as yxf. In fact, what happens is that the difference between the two, that is xyf minus yxf, is in fact the Lie bracket xyf. All right. Now the same question can be posed for covariant differentiation. So now I think of dxy minus dyx. Okay. So that too is not the same. Dxy may not be equal to dyx in general. So what we do is to get hold of the difference, what exactly will be the difference, we introduce a tensor. We introduce a tensor. And this tensor I will be taking as a vector valued function. So introduce a tensor Txy. And I will be calling it a torsion tensor. So formally speaking, let me write down the definition. A vector valued, this is the definition, a vector valued tensor, a vector valued 2 form rather, it is skew symmetric, so it is a special tensor, a vector valued 2 form on a manifold a vector valued 2 form, let me denote it by the symbol T. A vector valued 2 form T on a manifold M defined as this, T of xy equal to dxy minus dyx minus Lie bracket xy. Vector value 2 form T on a manifold defined as this is called the torsion of the connection D, is called the torsion of the connection D. On a manifold M. It's called the torsion of the connection D on M. So what I am saying is, that is, for every pair of vector fields, pair of vector fields x comma y the torsion T at xy, T of xy is a vector field. Defined by the above formula. Defined by the above formula. One can notice that dxy, dyx, Lie bracket xy, all the terms in the right hand side are vector fields, and therefore the value of t on the pair of vector field is a vector field. That is why I said it is a vector valued function. And moreover, it is a two form because it is operating on a pair of vector fields. Alright, now there are some other observations. Number one, so as a property of T we can notice, so properties of T. So there are some obvious things that you can notice from the formula of Txy. One thing is that it is skew symmetric, which is obvious from the definition itself. We are calling it a two form. Therefore, it has to be Txy minus Tyx. Number two, if you replace x by a function f by a vector field fx and y by gy, then you will see that f and g both will come out. Verification is easy. For the first one, just look at the formula of T. You will notice that if you replace x and interchange x and y, then this term will become dyx, this will become dxy, and this will become Lie bracket xy. So you can see, if you compute dyx, tyx, it will be dyx minus dxy minus Lie bracket yx. Now, if you take minus common from here, it will become dxy and this will become dyx, and Lie bracket yx is in fact minus times Lie bracket of xy. So, it is minus times Lie bracket of xy. Okay? Because Lie bracket xy, everybody knows, is minus times Lie bracket yx. So, we have used this fact, and this is nothing but T of xy. So, skew symmetry of T is obvious. For the second one, second property, you can see what you do is to verify the second property, I will simply look at T of fx comma y. So, this I can write down by definition, it will be written as dfxy minus dyfx minus Lie bracket fxy. Now, we have a property of the connection that whenever you have fx downstairs, f comes out. So, the first term will be f times dxy. For the second term, you have a formula which says that it is equal to yfx plus f times dyx. This is the second term. For the third term, if you remember, there is a formula for Lie bracket fxgy. This is equal to fg Lie bracket xy plus f times xgy minus gyfx. Make use of this formula for this term. So, it will be minus times, let me write down this term here. So, it is f times Lie bracket xy, then plus f operating on xg, but g is 1. So, x operating on 1 will be 0. Is it right? X operating on a constant function is 0. So, the second term will go off, second term will go off 0, and then you have minus g means 1 yf into x. Okay. Now, rearrange these terms. This is f times dxy minus yfx minus f times dyx. Then you have minus f times leave bracket xy and then plus yfx. Yfx and yfx will cancel each other here. And what you get is the following: f times dxy minus f times dyx, and you have minus f times, okay, minus f times leave bracket xy. That's all. These are the terms that you have. If you take f common, you will be getting f times dxy minus dyx minus leave bracket xy. So, this is f times t of xy. So, the first property, second property is verified when you have only function sitting here. Now, the same way you can verify that t of x gy, g will come out. So, I can rewrite down this as t of minus times t of gyx by property number 1, and by this part of the property you can write it down minus g times t of yx, and this is g times t of xy. So, I need not verify it separately. So, combining these two, I will say that f and g will come out if they are sitting with x and y respectively inside the bracket of t. So, this verifies. This verifies property number 2. All right, when okay. Now, strictly speaking, when you talk of tensors, you won't call it a tensor, because for you a tensor is a map from the product of tangent spaces into R, but here this is not the case for torsion T. So, look here, but what can I do? I can regard this object T as a tensor also. So, T can be viewed, this is a note. The operator T can be viewed as, a 1-2 tensor, 1-2 tensor. On M. How? That let me explain you. I will define a map, let us say T bar. So, define a map T bar. Define a map T bar as follows. So, T bar I am defining as a map from the tangent space, rather dual space, product tangent space, or you can call it chi m, does not matter, into R or into C infinity m. If you are working locally at a point, then you consider the set of real number over here. Otherwise, if you are working globally, that space, the range space, is a space of functions. So, what T bar will do, it will operate on a one form and a pair of vector field xy to produce a function, and that function I define as omega operating on t of xy. T is already there with me. So let me write down my statement. Let me improve my statement, this one, the first line. Given the torsion T, given the torsion T, define a map, define a 1-2 tensor. As follows. Now, corresponding to every t, you can find out a t bar, and corresponding to every t bar, you can find out a t, and that means t and t bar have a 1-to-1 correspondence. What I am saying is, for every t, you can associate a t bar, and if you have a t bar defined like this, then you can find out a t over here. All right. So that means there is a 1-to-1 correspondence between t and t bar. T and t bar have a 1-to-1 correspondence. So what we do, we identify t with t bars, and therefore we can identify t and t bar, and therefore by the abuse of language we call t to be a 1-2 tensor. Strictly speaking, t is not a tensor, but if you identify it with t bar, it will be considered as a 1-2 tensor. We identify t and t bar and call t a 1-2 tensor. Alright. So a torsion is a 1-2 tensor on M defined by the box formula. Alright. Now locally, how does it look like? So locally, if I consider a coordinate neighborhood uxi on M is a coordinate neighborhood on M, then what we do is we can look at the local expression. This, and if we denote t of del over del xi del over del xj by the symbol, since it will be some scalar time del over del xk, so that scalar I will choose as tk_ij. Here ij is corresponding to this I and j comes out into del upon del xk. So this is what these. So these are the coefficient of the 1-2 tensor T. Now how these coefficients will be defined, we can see by formula. So by formula, t of xy you are denoting by using t of xy is equal to dxy minus dyx minus Lie bracket xy, where d is a connection on M. Now if I replace x and y by these basic vectors del upon del xi and del upon del xj, then you can see what happens. Del upon del xj equal to d of del upon del xi del upon del xj minus d del upon del xj del upon del xi minus Lie bracket of basic vector fields, you know is 0. So, this last term goes off for basic vector fields. This quantity you are denoting by Tkij. So, Tkij del upon del xk, and the right side will be Christoffel symbol Ijk del upon del xk minus this will be Ji k del upon del xk. So, what do you notice from here is the following. So, from here you see that Tkij is equal to Christoffel symbol Kij minus Kji. Okay. So, this suggests a definition. We will say that the connection is symmetric if its torsion is 0. So, here follows a definition. We say that the connection D, a connection D on M means a manifold, on M is symmetric, if its torsion is identically 0. That is, T is identically 0. And from the local expression you can notice if T is identically 0, its component coefficients will be 0, and therefore Kij will be equal to Kji. In this case, Christoffel symbol or coefficient of connection will satisfy the symmetric property. This follows from the above formula. All right. And one thing more, in this case, number 1, this will happen, and number 2, what will happen? If you look at the formula number 1 of the torsion, what happens? By formula number 1 of the torsion, you know that Txy is equal to dxy minus dyx minus Lie bracket xy. Now, if torsion happens to be 0, then what will happen? dxy minus dyx will be equal to Lie bracket xy. So, at number 2 you will say the torsion is 0, the torsion is 0. Torsion is 0 means torsion of the connection is 0 if and only if dxy minus dyx is equal to Lie bracket xy. All right, okay. Now the next thing is the curvature perhaps. So the next thing is the curvature. So straight away I will start from the definition. So what happens is, so given a pair of vector field xy, there are two vector fields x and y. To this pair of vector fields I will find out a map. I will call it Rxy. So, Rxy is not a function, it is a map in fact on the space of vector fields. So, I define my R in such a way that Rxy is a map from where to where? From chi m to chi m. So, Rxy will operate on Z, on a vector field Z, and it gives you the following. It gives you dx dyz minus dy dxz minus d of Lie bracket xyz. So, I define Rxy by this formula. So, to a pair of vector field, we consider a linear map. You can see it later that it is linear. So, to a pair of vector fields, x y on a manifold M, assign a vector field Rxy, to a pair of vector field xy on M, to each pair of vector field, xy on a manifold M, assign a vector field Rxy, assign a linear map, assign a map, not a vector field, Rxy from where to where? From chi m to chi m. Satisfying the following formula, satisfying the formula I am writing down, satisfying the following. Let me write down. Rxy will operate on Z and will give you a vector field Rxyz. And this Rxyz is given by dx dyz minus dy dxz minus d of Lie bracket xyz. This is the defining formula for Rfxyz. If you want to write down Rxy, expression of Rxy, you can write down Rxy equal to dx dy minus dy dx minus d of Lie bracket xy. So, what we are doing here is we are looking at the commutativity of the differential operators. So, in the beginning, this difference is measured in terms of Lie bracket, but since it is an operator, so it is given in terms of an operator d. Okay. Now, there are some characterizing property of the operator Rxy. So, let us look at these properties. All these properties will be verified.
So, what is it called,
Rxy, we will be calling it a curvature tensor. Let me write down. The map Rxy, the map R. अब देखिए द मैप R. अब इसको मैं अभी थोड़ी देर में साबित कर दूंगा कि ये एक टेंसर है, लेकिन फिलहाल लेट मी कॉल इट ए मैप. द मैप R is called the curvature tensor. R is called the curvature of the connection डी। अब दोनों ही चीज़ों के लिए, टॉर्शन के लिए और कनेक्शन के लिए, आपने टॉर्शन के लिए और कर्वेचर के लिए, दोनों के लिए आप देख रहे हैं कि ये एसोसिएटेड हैं कनेक्शन से। एंड कनेक्शन इज़ नॉट ए यूनिक थिंग। On a manifold we can have several connections. So when you change the connection, the curvature and torsion both will change. So that is why we call it a curvature of a connection D. Now the properties are the following. The map R is called the curvature of the connection, and it has the following properties. पहले ये दिख,
In the same sense, we are talking that we have a curvature of a surface. So here we have a connection.
वी हैव ए कनेक्शन। वहाँ पे डिफ्रेंशिएशन जो है एक ही किस्म का होता था और वो Rn से आता, R3 से आता था। यहाँ पे वो डिफ्रेंशिएशन नहीं है बल्कि कोवेरिएंट डिफ्रेंशिएशन है। तो कोवेरिएंट डिफ्रेंशिएशन के टर्म्स में ही आपको कर्वेचर भी डिफाइन करना पड़ेगा। अभी जब मैं इसका लोकल एक्सप्रेशन आपको दिखाऊंगा तो आप देखेंगे कि वो एक्सप्रेशन सेम आता है जो सरफेस के केस में आता था, वही कर्वेचर है। लेकिन यहाँ पे कर्वेचर को एज कर्वनेस ऑफ द मैनिफोल्ड देखना ज़रा मुश्किल है इनिशियली, बट व्हेन यू विल एक्सप्लोर इट मोर एंड मोर यू विल गेट द आइडिया कि येस इट्स ए इनवेरिएंट ऑफ द कर्वनेस ऑफ द मैनिफोल्ड। ओके, बट इट विल बी रियलाइज्ड लिटिल लेटर। All right, so the map R is called the curvature of the connection. So what I will be doing, I will be, now let us look at properties. First look at the properties. Properties of the curvature. Number one, R of xy is equal to minus times R of yx. R of xy. It is skew symmetric in the first two slots. Only two slots are there, so it is skew symmetric. And number two, these are the two main properties. Number two, if you substitute x and y by fx and gy, and if you put h over here, there are three vector fields that are associated. So all of them will come out. F will come out, G will come out, the function H will come out, and R of x, y, z. Where FG, where F, G and H belongs to C infinity M. The first property is easy to check because from here you can see that if you interchange x and y, this will become dy dx minus dx dy minus leave bracket yx. So if you compute from here, I am verifying the first property. So use this formula. So R of yx, what will be R of yx? It will be dy dx minus dx dy minus d of leave bracket yx. माइनस कॉमन ले लीजिए तो ये हो जाएगा, ये प्लस का हो जाएगा dx dy माइनस dy dx, ये हो जाएगा प्लस डी ऑफ ये वाई एक्स वाई के बराबर होगा। नहीं, अभी तो माइनस ही रहेगा ना।
सर दो प्लस है, एक माइनस, ठीक है सर।
वाई एक्स ही रखिए, ठीक है ना। अब ये जो है आप देखिए, इसको मैं प्लस कर देता हूँ। So this is equal to ryx, ओके। माइनस बाहर लिया तो ये प्लस हो जाएगा, ठीक है, ठीक है ना। तो अब व्हाट आई एम गोइंग टू से इज कि दिस इज इक्वल टू, इसको मैं एक्स वाई करूँगा तो माइनस हो जाए, तो इट इज़ इक्वल टू माइनस टाइम्स डी एक्स डी वाई minus dy dx, and now I can rewrite it as minus times d of Lie bracket xy. Now this quantity in the bracket is minus times r of xy. This quantity in the bracket is r of xy. So this proves that r of yx is minus times r of xy for all xy. So first property is easy to check. To check the second one, I will do the same. I will verify it only for one function. So r of property number 2. So consider r of fxyz. ठीक है ना? So by formula, this quantity will be equal to d of fx dyz minus dy dfxz minus d of Lie bracket fxy z. Now simplify it. So this f will come out by the property of connection, dx dyz minus dy. This f will sit over here, f of dxz minus d of this. I can once again use the formula of Lie bracket fxgy. So this is f of xg, z will be 0, g is 1, so xg will be 0. So minus yfx and plus f of Lie bracket xy z. ठीक है? Now the first term you keep as it is, minus. अब आप you can view it as if dy f times a vector field dxz. So make use of the formula dx fy. ये y टाइप की चीज़ है. So it is equal to yf dxz. ठीक है ना? ये होता है xfy plus f times dxy according to the formula number 4 of the connection, and then minus once again f out dy dxz. Okay. Now it is distributive in this slot, so it will be plus d of yf को भी ऊपर लिख लेते हैं, dxz. This minus will make it minus, so minus f को ऊपर लिख लेते हैं again, Lie bracket xy z. Keep this term same. Yf dxz appear with opposite signs, so cancel them out. What is left is f is common in all the three terms, so take f out. What you get in the bracket is dx dyz minus dy dxz minus d of Lie bracket xyz. And this is nothing but r of xyz. So if f is sitting in the first place with x, it comes out. Now the skew symmetry suggests that if it is sitting over here, it will also come out by the same argument which I gave earlier for the torsion. So if you have g sitting with y, let us say r of x gy, इसको बंद कर दीजिएगा, gyz. Okay. So it was equal to minus times r of gyxz, and g should come out by last proof. So minus g times r of yx z. And now if you interchange x and y, minus sign will come, so it becomes g of rxy. So what you see that if whether a function is sitting here or sitting here, it comes out. Okay. So we have verified both of these. Now the last is little different. Now consider, so this implies that r of fxgy is equal to fg of rxy. Now for the last case, what I will be doing, I will put xy over here, and here I will put fz. Okay. So consider now this. So this, according to the formula, is dx dy fz minus d of y dx fz minus d of leave bracket xy fz. So you simplify it. So dx dy fz, इसको सिंप्लीफाई कर लेते हैं, तो ये हो जाएगा y fz प्लस f टाइम्स dy z माइनस dy dx fz, इसको भी ऐसे ही कर लेते हैं. So this is x fz प्लस f टाइम्स dxz माइनस, इसको फॉर्मूला लगाइए. सो लीव ब्रैकेट एक्स वाई ऑपरेटिंग ऑन एफ इंटू जेड. ओके. एंड देन वंस अगेन माइनस what? F times leave bracket of x y z. Good. Now you rearrange the terms. So rearranging, so क्या होगा? So d first term, look at the first term, dx operating on yfz. So yf is a function. You look at it as if it's a function g. So x operating on g into z. So this is x operating on g means yf into z. Plus the function g is out dxz. So plus yf is out dxz. Okay, so the first term is resolved. Come to the second. So what is second term? dx operating on f dyz. ऐसा है, dx operating on f times dyz. यही है ना? So how would you deal? xf. So plus or minus? हाँ, plus xf dyz. Okay, plus f out dx dyz. So this term is resolved. Similarly, you can resolve the second term. So minus y operating on xf into z. Okay, once again minus yf is out. Sorry, xf है ये. xf is out dy z. ठीक हो गया? Come to here. So this is minus yf dxz. Okay, minus f out dy dxz. Okay, ये वाला भी हो गया. yf dxz minus f out. Okay, both the terms. Now come over here. So इसको भी मैं simplify कर लेता हूँ by formula of leave bracket. So this is minus x y f z and minus plus y x f z. ठीक है ना? and then minus f times Lie bracket d of Lie bracket x, y, z. So all terms have been resolved. And now see what are the terms which are cancelling. So x, y, f, z are cancelled out. y f dx z है कहीं? ये है. y f dx z are also cancelled. ठीक है. अच्छा, y एक्सेप्ट z ये कहीं है? ये है. y एक्सेप्ट z and y एक्सेप्ट z, they are cancelled out. अच्छा, अभी एक और भी, x f dy z, yes, third term will cancel this term. Now remaining term you write down. So f is common among the remaining terms. So first term is here, f times dx dyz. The second term is here, minus dy dxz. And the last term is d Lie bracket xy z. So you have got f times r of xyz. So if f is sitting with z, it still comes out. So wherever you make your function to sit, here, here or here, every time it comes out. So this is the property. So if you combine all of them, you will say that r of fx, gy, hz, then all of them come out, all these functions multiplied by rx, yz. So the two properties, two algebraic properties of the curvature tensor have been verified. All right. At other things like local expression, etc., we will discuss in our next lecture. I stop at this point.